Swayam Prabha. Digital India. Educated India.
In the last lecture, we had discussed the dynamics of membrane, a flat membrane, and today we are going to carry forward our discussions on this and look at the vibrations of a rectangular membrane. So, just to recapitulate what we discussed in the last lecture, let me write down the general mathematical formulation of a flat membrane. So, we had derived the equation of motion of a membrane with density per unit area or the areal density mu undergoing small transverse vibrations where this W is the field variable which is a function of x, y, t, or W could be in the polar coordinates, for example, could be function of r phi t, and nabla square is the Laplacian. So, in the case of rectangular membrane, so in the Cartesian coordinate system, nabla square is double derivative with respect to x plus double derivative with respect to y. In the polar coordinates, nabla square is double derivative with respect to r 1 over r single derivative with respect to r plus 1 over r square double derivative with respect to phi. So, we have this Laplacian operator in two coordinate systems, and along with this we have boundary conditions. So, we can have a fixed boundary or a sliding boundary So, this is the force per unit length T times the gradient of the field variable dot the unit normal at the boundary. So, for example, for the rectangular membrane which we are going to discuss today, and we will assume that the boundaries are fixed. So, let me first so we have W at x equal to 0, which is the y axis, and for all y and all time at x equal to a, for all x at 0, which is the with y equal to 0, which means the x axis, so this is our mathematical formulation for this rectangular membrane. So, we are going to look at the modal vibrations of the rectangular membrane. So, let me write down so we are interested in a solution as we have discussed before. So, this is separated in space and time. So, we have this spatial function W, which is a function of x and y, and the complex time function. Now, we substitute this solution form in the equation of motion, and also the boundary conditions. We obtain, so upon simplification, so this is our eigenvalue problem. Where of course, this Laplacian is once again the double derivative with respect to x plus the double derivative with respect to y. So, in order to solve this, let us consider the solution of this differential equation of the eigenvalue problem as some constant exponential I times alpha x plus beta y, where alpha and beta are as yet unknown constants. So, if you substitute this solution form in here, since we have double derivative with respect to x, so that gives us alpha square minus of alpha square minus of beta square from the double derivative with respect to y plus. So, this is what we obtain. So, alpha and beta have to be chosen such that this equation is satisfied, but that is not all. As you know that we have to also satisfy these boundary conditions. So, we expect the solution in the form, let us say, since we have considered separable solution even in x and y. So, I can write this is y. Okay, so, this may be simplified and written out like so, I am multiplying out and redefining these products as A1, A2, etc. So, we have this as the general solution of the spatial function w x comma y. Now, this general solution must also satisfy the boundary conditions, which are going to give us further conditions. So, let me substitute this solution in the boundary conditions. So, you can see that so this boundary condition would imply so x is put as 0 . So, this follows from this term, and here it is sin alpha x, sin alpha again sin alpha x here. So, at x equal to 0 these two terms vanish. So, we are left with this. Then let me take this boundary condition. So, at y equal to 0, so this term will vanish and this term will vanish. So, this these are the two conditions I obtained from these two boundary conditions. Now, it is very easy to see that these two boundary conditions imply, so for all y and all x, so for all y this condition should be true, which immediately tells us that a1 and a2 must be 0. And this also tells us that a1 and a3 must be 0. So, a1, a2, a3 are all of them are 0. So, we are left with only a4. So, which means in order to satisfy the boundary conditions, let me call this only a, since there is only one term in this function. And we are left with two more boundary conditions. So, these are so when I substitute replace x by a, and the fourth one now again this condition should be valid for all y and this condition should be valid for all x. So, this should imply that sin of alpha x should be 0, since a cannot be 0. So, therefore, alpha must be m times pi over a. So, this gets indexed and there are infinitely many values of alpha m, and similarly from here this gets indexed by n, and there are infinitely many values of beta n. So, then finally, we recollect that alpha m square plus beta n square must be equal to omega square over c square. Now, this should also therefore get indexed. I will write as m comma n within brackets. So, I can take this pi as well outside, So, it is square root of m square over a square plus n square over b square. So, that is, these are the eigenfrequency of the rectangular membrane. Okay. So, and then we obtain from this function the eigen functions, which should also now get indexed. So, these are the eigen functions. Of course, here we have these infinitely many eigen functions. Now, here you can notice that the higher, so the fundamental eigen circular eigen frequency is obtained when m and n are 1, and you can see that higher circular eigen frequencies are no longer just integral multiples of the fundamental, what we have seen in strings. So, in the case of strings, suppose I simply block this, then you obtain actually the eigen frequencies of the string. So, there you have seen that the higher eigen frequencies are just integral multiples of the fundamental frequency. Now, in the case of the membrane, this is no longer true. There is another possibility that we are going to discuss shortly, and that is when m square over a square plus n square over b square is some r square over a square plus s square over b square. So, that is a possibility. That means, there are two different modes which have the same circular eigen frequency. So, that we are going to discuss shortly. So, before we discuss, so here let me just tell you about the orthogonality of these eigen functions. So, which is very clear from these expressions. So, this inner product, which is defined as the integral over the domain of the membrane and we know from these trigonometric functions, properties of these trigonometric functions, that this is nothing but so for example, the integral of this over x from 0 to a is a by 2. Similarly, this is b by 2. So, this is a b by 4, but then that happens when m is equal to r and n is equal to s. So, these are Kronecker delta functions. So, this takes a value 1 only when m equals r, and similarly this takes a value 1 when n equals s, otherwise they are 0. So, this is the orthogonality property of the eigen functions. Now, before we move on, so let us have a look at some of these eigen functions. So, here I have plotted 4. So, this is the fundamental, which is with m equal to 1 and n equal to 1. So, there are no nodal curves in this mode. Here this is m equals 1 and n equals 2. So, there are 2 lobes here. So, m is for this direction, n is for this direction. So, we have one nodal line along so this is parallel to the x axis. This is for 2 1. So, one nodal line parallel to the y axis, and this is m equals 2 and n equal to 2. So, this is the w 2 comma 2 mode. So, you have 2 nodal lines like this. Now, the general solution, so this eigen functions can now be used for constructing the general solution of for any problem related to the rectangular membrane. So, let me write out the general solution. So, here motion of the membrane, the general motion of the membrane may be written as the summation over now all these constants that I introduce, we have these indices m n. So, this is the general solution, which can be used for solving the initial value problem, and here these constants, they are determined from the from the initial conditions. Now, in order to do that, we have to use the orthogonality property. So, the initial conditions will be in the form so the initial configuration or the displacement of the membrane and the initial velocity distribution. So, given these two functions capital W naught and capital V naught, then we can write this, and similarly for the velocity condition. We have this. So, we can solve now for these infinitely many coefficients C and S using the orthogonality property that we have just now discussed, and we have discussed this procedure in a previous lecture as well. So, we can determine these constants and finally construct the solution using the summation. Now, let us consider this situation. We have an interesting property called so here what we have, let us look at the expression of the circular eigenfrequency, which reads like this. Now, suppose you have this ratio A over B, let me call it the length ratio. Suppose this is a rational number. So, if this is a rational number, in that case we can have two integers a b such that equals the length ratio. Now, when this happens, then we can have an interesting possibility that, so we have this possibility m square plus L r square, this ratio square, for a different number r and s, different integers, if this equals this. So, once we have this, we have defined this ratio. So, I can write this as so I can express this in this form in terms of L r. So, now if for two so for a given m n, if there exists another mode with r and s such that these are equal, in that case we have two identical eigen frequencies, circular eigen frequencies. So, there are two modes with identical circular eigen frequencies, but then remember that the eigen functions, they will be orthogonal, they will still be orthogonal. So, we have two modes with identical circular eigen frequencies, but orthogonal eigen functions. Now, this is an interesting occurrence. Now, let us see an example. So, for example, if a over b, which is L r, is 3 over 4. In that case, if you take m n as 5 3 and r s as 4 5, then you can easily check that for L r 3 over 4, these two give identical circular natural frequencies. But their eigen functions are orthogonal. Now, this is an interesting situation. So, let us understand. So, this is known as modal degeneracy. So, you have identical eigen frequencies, but distinct eigen functions are orthogonal. Eigen functions. So, let me graphically try to depict this situation. Now, we have been discussing this visualization in various contexts. So, let us consider the modal space of the membrane. So, this is the modal space or the configuration space of the membrane. So, the axis, so which I have drawn perpendicular to depict orthogonality. So, for example, this is, let us say, W11, and then this is, let us take the example that we have just now considered. This is W53, and again there are many such axes which are orthogonal to one another. I am only drawing 3, and you have to stretch your imagination a little bit. So, in this modal space in which I have drawn only 3 of these orthogonal eigen functions, you see this is an eigen function corresponding to omega 53. Similarly, this is 1 and this is, but this is same as omega 53. Now, if this is an eigen function corresponding to omega 53, then this is also an eigen function corresponding to omega 53. So, therefore, any linear combination of these 2 eigen functions is also an eigen function of omega 53. So, anything that lies in this plane so this is the W45 W53 plane. So, anything that lies in this plane, any vector, any function that lies in this plane is also an eigen function of omega 53. So, we have some kind of an isotropy in this modal space. So, this plane is isotropic, any function on this is an eigen function. So, this property is completely missing in the case of strings. So, in strings, for example, we do not have modal degeneracy, we do not have this property at all. So, this is one distinction of a membrane from a string. So, once again this space which is spanned, this function space which is spanned by these 2 eigen functions, the membrane dynamics is isotropic in this. So, so imagine that you are exciting this membrane close to omega 53. So, you can expect the solution So, the solution would be something like this. So, this can be written as now. You can imagine that these two, so these two frequencies are actually one and the same. Now, it depends on how the two modes have been excited. So, what will happen is, since the combination of, so now the actual solution is a combination of these two eigenfunctions, but then this is the mode corresponding to a single frequency omega 53, but these two modes are distinct. So, what is going to happen is, you are going to see a combination of these two modes appearing in the vibrations of the membrane, and it may so appear that the membrane is vibrating in an unsteady manner, because it might be switching from possibly this mode to this mode, or a combination through a combination of these two modes. So, that you can understand from this solution form. So, because of this isotropy of the modal space, we have this kind of a phenomenon. So, for example, if you excite this in a certain manner such that since 4 5 is same as 5 3, suppose the excitation initial conditions have been set such that this is the solution, let us say. Now, in that case, since one is cos, the other is sine, so at time t equal to 0, you have this mode. You can see the nodal lines corresponding to this mode, and at time 2 pi by omega, you have this as 0 and this is active. So, you will see the number of nodal lines corresponding to W 4 5. So, it is going to continuously make transitions from W 5 3 to 4 5 and back. So, but this is a modal solution. So, you will actually see changing profile of the membrane. There is no fixed nodal lines. So, they keep varying according to this, but suppose the excitation is cos. In that case, you there will be a fixed combination of W 5 3 and 4 5, which will be C times W 5 3 plus S times W 4 5, because this will be cosine, this is also cosine. In that case, that will come out, and therefore, you have a fixed kind of a shape of the membrane vibrations. So, this is an interesting feature of modal degeneracy, which is present in membranes and not in strings. So, in this picture I have shown this for a square membrane. Interestingly, for the square membrane, you see the so with side equal to a, in that case this is m square over a square, n square over a square. So, that comes out. So, square root of m square plus n square. So, you will find that omega m n is equal to omega n comma m, where m not equal to n, and then these are degenerate modes. So, all modes with m not equal to n are degenerate modes. For the square membrane. So, for the square membrane, for m not equal to n, these are all degenerate modes. So, once again let us have a look at this picture. So, here we have this combination. So, the combination I have written like this. So, I have written the combination like this for the 3-1 mode. So, let us look once again at this picture. So, here when delta equal to 0, so you will find it is only W31, and here it is a value pi over 25. So, you see a combination of 3 1 and 1 3, this is still a higher value of delta. So, this combination changes at pi over 4, this combination of 3 1 and 1 3 gives us a nodal curve which is like this, and this changes for if you increase further to this, but rotated, then this rotated, and then this rotated, which means the nodal lines will be horizontal for delta equal to pi over 2. So, you see the when a square membrane vibrates in this combination, then you will see the nodal patterns, nodal line patterns changing continuously through these shapes. So, you will not see a steady nodal line picture on the membrane. So, the nodal lines will be kind of unsteady. So, this is something very interesting that you can observe in an experiment. So, to summarize, we have looked at the modal vibrations of a rectangular membrane, and we have observed a very interesting property, which is the modal degeneracy. Some of these aspects we will discuss further in our next lecture. So, with that I conclude this lecture.